A key idea of Lab 5 is for you to actually write some part or most of the code for a simple model on your own. Try your own ideas out a little bit. Now this lab, my recording of it will show you a specific example approach. I'll talk through that approach. But really the goal here is not for you to just mimic and copy that code and go, oh yeah, I ran that model, but rather to try to think, how would I model this, and write at least some of the code yourself. Infectious disease transmission models or diffusion models as a more general class often use the concept of SIR, where S stands for susceptible, I is infected, and R is recovered. And while this can be used for the obvious things like viruses and other diseases moving through a population, it can also be the transmission of ideas, the adoption of new products, many other things. Usually these models, the simplified versions, start with most of the individuals being in the susceptible state and just a few infected individuals, and then we watch how that infection travels through the system. As they make contact, then there is some probability that the disease will be transmitted. Although there's a lot of different ways to do this. And in the simplified cases, and of course you can imagine many extensions, you would have the people recover at some point, and maybe in the simplified assumptions they would remain immune to the disease and would no longer transmit or have the symptoms. Of course you can have lots of other outcomes, and this is just a basic building block really. But before we dive in, let's think a little bit about some of these options. You could use a patch to represent a city block. You could keep track of how many people were on that block, how many of them were infected. You wouldn't have to really model the pathogens at all, so you could have a cellular automata version, a lot like the forest fire model. The trees catch fire, catch the neighboring trees on fire. Almost the exact same logic could be used and reclassified as a disease transmission model. And you could do really good analysis with such a model. Also, you could do, of course, the obvious thing is to model people as agents, and you could then have multiple people on a patch. Again, the patch could represent like a city block or something like that. It doesn't have to be that way. Agents can have properties, and so you could have an agent that had a property of whether or not it was infected, and then the pathogen wouldn't need to be modeled directly. If you're going to model the contagions, are you going to have a lifetime so a contagion lives kind of in the environment, and if it happens to contact an infectable or susceptible person, then the disease would transfer to them, and then the pathogen might die at that point, or maybe the pathogen lives on and goes on to infect somebody else. It depends a lot on the particulars of the biology of what's going on. So you can imagine a lot of different levels of complexity. So in the end, you then need to think about how you're going to visualize it. So do you use colors, or do you make the agents do something, change their size, change their, so there's just some questions about how you might visualize it. The simplest way is to just use colors, and in this case maybe you would say that if they're susceptible, they're yellow, if they're infected, they're red, for example, and blue is sort of a smiley face color might be recovered. Anyway, you can think about that. And delving into the idea slightly deeper, how will the individuals or the groups of individuals, if it's a city block and you're not modeling them explicitly, how do you change? What causes the state to change from susceptible to infected, from infected to recover? So let's take a look at that first state. What factors might you want to take into account? Do you need to know something about the total number of people or the density of people on a city block to determine infection? We need to know something about the disease. How infectious is it? How frequently do people in that block contact each other? Is it an isolated community where people almost never see each other? Or is it a business building where there's constant interaction between general public who might be coming in with infection, etc.? Is it a school? Obviously, that's a very likely place. So depending on the situation, what we're specifically trying to model, we have to think about how does the infection occur, basically. And then once they're infected, is it just the passage of time? It takes so many days for the disease to incubate, and after that the person's no longer infected, and then they are recovered and they would change the state? Or does the presence of other people who are infected change the time course of the disease? How much individual characteristics do we want to take into account? Some people are fast at recovering, some people are slow. Do we just use a random number? Lots of things to think about. And just the final thing, before you really dive in, you ought to think, well, am I really trying to create an accurate quantitative model that could really predict numbers in order to make policy decisions? Or am I more just trying to explain how disease works and sort of teach some of the concepts of epidemics and things like that? And either of those goals would be fine, of course, but it might affect how much detail you go into in different parts of the model. And let's use this as a chance to explore the Railsback and Grimm's ODD framework. That's objective, design, and details. So the objective here might be to demonstrate, rather than quantitatively predict, the process of disease spread. And we want to focus perhaps, therefore, on the contagion, since that's what people might want to understand a little bit better about. And the actions could include the moving of the contagions, the infection process, if there's lots of hosts available. If there isn't, then maybe the contagion dies without ever finding a host. Some of the design concepts is mostly going to rely on the basic ones. There's not a lot of fancy stuff in this particular, or isn't necessary for our purpose in building this model. So the contagion might move around rather aimlessly and infects a host. If they're easy to bump into, a high probability, you might have some infection take place in a host. So the details, what do we need to do? We need to talk about starting conditions. We would start with, say, 3 and some number of contagious agents. We might make that a slider. We might randomly assign some number between 0 and m, some other number that's on a slider to represent the number of hosts that are available on a given patch. Patches have different numbers of hosts or different densities of hosts. We might have a fixed contagion lifespan of so many ticks, y, another parameter that we set in the model. And the main subroutines that we have to think about and write the code for is how does infection work? How does the disease spread? And what happens or what causes them to die? And does anything happen at that point? Now, although I'm going to show you a specific example model, I'd love for you to say, how would I want to do this, and try to write a few lines of code and see if you can get them to work. You could borrow logic. A lot of the infrastructure for it could come from the FIRE model or some other model. You might borrow some of the code that I'm showing you and say, I don't really like that one. That one doesn't make any sense to me. I want to do it differently. So please do that. Push yourself a little bit. Use this lab as a safe place to try something out. If you're unsuccessful, you can go away and say, what do I need to study next? Maybe I need to go back and reread some stuff. Or maybe you just move on ahead and figure out how to get it working. Maybe you ask for some help. I'd be happy to do that. And start maybe on scratch paper, noodling on some lines of code, looking stuff up in the NetLogo dictionary and saying, how would I do this? Okay, I think I know how to do that. I think I saw an example of that. Get some stuff written, put it in, and see what happens. You're going to probably get some errors. That's okay. See if you can fix them. And see if you can convince yourself that the logic you wrote is working. So here's a simple example model. Let's just talk through it. The patches own a population size. How many hosts are on each patch? The turtles have an age. The turtles in this case are the contagion, and we need to know how old they are. Now, we could call them contagion. This model it calls them, they're referred to, the number of them is referred to as pathogen number, but we didn't bother to set up a breed called pathogens. We certainly could have. So the setup routine clears all, as always. It creates a number of turtles based on how many pathogens are going to be in the model. And then we ask the turtles to set their color to red. So red in this case means pathogen. We set their heading randomly, and we set the patch color that they're on to red as well. Then we ask the patches, all patches, to set their color to yellow set their population size randomly based on the average times 2, so they're going to be uniformly distributed over the different sizes of populations. We're going to reset the clock, and that's the end of the setup procedure. The infection process says if we have more than 10, it's a real simple model, if we have more than 10 hosts on a patch, then we run the spread routine, which we'll look at in just a second. We set the age to age +1, that's aging the pathogens. We check to see if it's time to die. That's another routine we'll look at in just a minute. We set a random heading for the contagion. They randomly wander around, and then we run the spread routine. That's the end of the go procedure. To spread, we ask if the patch color of the patch that I'm moving to, pointed at, which is patch ahead of me on my heading by 1, is yellow. Then we hatch a new pathogen on that patch. We spread to that patch. We go forward 1. We set our heading random, and we set the patch color to red because there's now a contagion there. And we set this new hatchling to have age of 0. And then that's the end of the spread routine. And the final routine that's needed is to check die, see if it's time to die. If age is greater than lifespan, then we set the patch color to blue and die. Blue means recovered, basically. In this case, the pathogen has ended on this patch. So that's a really simple model. You'll have to think about some of those things, just like, would I have written it this way? And I really encourage you to think, okay, maybe I can make sense of this one. We'll go through this. I'll do a little demo on this one just for fun. And but you might think about, wow, I would do it way differently. I like the pure cellular automata way of doing it. Or I want to have people and patches both as movable agents, or people and pathogens. Or maybe I only don't want to really model the pathogens directly. I just want to talk about how people spread disease to one another. If they're infected, they spread it. I don't really need to focus on the pathogen. So those are all viable things for you to do with this lab. All right, so here's the demo model, and I'm going to just kind of talk through it. You saw in the previous material, I talked about the fact that we would have some variables: the number of initial pathogens, the average population size per patch, and the lifespan of pathogens. We also have a reporter here, a monitor that just reports out the number of pathogens. That'll start at 1, of course, when we do the setup. Let's go ahead and demonstrate that. So we've got 1 sitting up here in the corner. That little red one is the pathogen, so we've got 1. And with these particular numbers, if we run the model, nothing happens. Gee, what happened? Well, it wasn't able to spread. And if I run it again, well, there's no more pathogens. They're gone. So, gee, I might have to increase the number of pathogens a little bit. So let me reset it up with a few extra pathogens. Now we've got them spread around a little bit on here. I'm going to bet you this one's going to move. And sure enough, the contagion spreads, and not everybody is infected. But in the end, a number of them were never touched, and are kind of around where the pathogens were. We see that the population got infected and then recovered. We can slow that down. But let's move over and take a look at the code real quick. This is the same code we talked about. So just to clarify, I sort of talked through that. We have the setup routine, we have an infection routine, and I'm hoping you could easily say, I think I'm going to do this differently. Again, the focus on this one is on pathogens, and then they're moving on an environment, and what's interesting is the environment has a state variable, which is the size of the population, number of potentially susceptible individuals on each patch. So sort of like a little city, kind of maybe more like a town where you've got some parts of the town. Nothing has super high density. The density varies from 20 people to maximum down to 0, or not the density, but the number of people. So I think it's pretty interesting to just look at this and think about what does this mean? If the pathogen has a lot longer lifespan, let me go back to 1 pathogen and leave things exactly the way they were. So we just have 1. The last time it didn't work. So if I go set up and run, one pathogen was enough this time. Isn't that interesting? Set up, one pathogen, run. Nothing happens. Why? Because it's sitting on a spot. Let's inspect that spot. So here's where we start to say, well, how does this model really work? We're going to right click. Notice we have no pathogens here anymore because it died. But let's inspect that patch after the fact, and there was just one population there, which is less than the 10. There wasn't 10 people here, so it couldn't spread. So now let's go ahead and close that monitor because it's going to end up being created somewhere else. If I create another one, and before we start, if I go over there and right click and inspect that turtle, that's my pathogen right there. And if I open it up, I can inspect that turtle. It has a current age of 0, and as I run the model, if I run it really slowly, okay, slow it down, its age goes up and then stops. But this time, the patch that it was on allowed it to cause an infection to start with just one. So just showing you the tools, you can use this inspect to try to figure out the logic. You could watch the patch, you could watch the agent, and sort of help figure out what's going on in this model. And again, I don't think I'm going to do too much else. You can play around with this model and try to figure out how it works, and I hope you really do this, try to write some logic on your own. And if you already started doing that and then you came over and looked at this video, maybe this will give you some ideas on what you might do to change your logic to get it to actually work the way you had hoped it would work.